Okay, let's start up. Today we're going to begin a 2-lecture section on exploitation and exploration. The idea is very simple. We've talked about it off and on over the course, but it's an important part of reinforcement learning because basically whenever you're making a decision, you could exploit the knowledge you have so far and choose the action that you currently estimate, although you could be wrong, currently estimate is the best action. Or you could invest in the future and do some exploration instead, and maybe you'll learn something that will, in later years, make you even a better exploiter. Right? So in any kind of learning system over time, there's this question of kind of a bird in the hand versus two in the bush or something like that. So the best strategy might, if you're going to plan to live for 100 years, might be to spend some time exploring in the early years so that you learn an even better policy to use in the longer term. And you see this everywhere. If you're going to a restaurant with your friends, you might figure out what's the best restaurant you know, or you might explore and try a new restaurant. By the way, I recently explored and tried a restaurant called Neither Fish Nor Fowl, which is a great restaurant in Pittsburgh. It's a little pricey, but if you want to go do something special, go explore Neither Fish Nor Fowl. It does have both fish and fowl, so I don't know what the name came from, but so you can do that. If you're drilling for oil, you can drill in the best region that you currently know of, or you could drill a well somewhere else. If you're playing a game, of course, you can play the tried and true strategies that you know, or you could try something weird and crazy and put yourself into a part of the space you haven't really previously explored. So today we're going to talk about a variety of approaches and some theoretical results about exploring and exploiting. And instead of telling you what they all are, let's just jump in. Now we're going to do this, and it really helps simplify thinking. We're going to do this in the context of bandit problems, which are really a special case of a Markov decision process that we've been talking about so far. It's a special case where there's no state. And so you can think of it this way. A multi-armed bandit is just a tuple of a set of actions you can perform. And you can think of that as like arms in a slot machine. Most slot machines actually have one arm, but you could imagine building a slot machine where there are K arms, and each arm has a different probability of paying off. And then you could have to play with that K-armed bandit. And we assume that there is some reward which is unknown to you at the beginning, just like in MDPs and reinforcement learning. So there's some probability distribution that is unknown to you, but that determines what reward you will probabilistically receive if you do a particular action A. And basically, that's what a multi-armed bandit is. So you notice it's just like MDP, except there is no state. Or put another way, there's only one state, and you're in it all the time, and every time you pull the arm on the bandit, on the K-armed bandit, it's the same distribution of rewards. So following, though, the MDP kind of framing, we'll say at each step, you have a sequence of times, and each time you can pick some action, and you'll receive some reward that's generated according to the probability distribution conditioned on the action that you chose. And your goal, just like in other kinds of reinforcement learning, is to maximize cumulative reward. Here we're not going to discount in this case, but and so the question generically is, what's the best strategy? And we're going to focus on exploring and exploiting. And a lot of the details here that we're going to talk about will be simpler because instead of talking about a full MDP with states, we're talking about this simplified kind of MDP, which is just a bandit. And, but still, the ideas that we talk about and the approaches, you can in fact see how you can extend those to MDPs as well. By the way, I didn't say this, although it's on the first slide. Chapter 2 in the Bartow and Sutton book is a pretty good description of most of the material that we're going to cover here. Okay, so just to make this concrete and to give us an example to refer back to, and this is actually out of Chapter 2, here's a way to think about a K-armed bandit. Suppose there are, in this case, 10 different actions you can perform. Each one of these horizontal indicated actions. And then there is a probability distribution on the reward that you'll receive if you do the kth action. You can see here these happen to be Gaussian probability distributions. Okay, but that's what the K-armed bandit problem looks like. And so now the question is, if I hid that slide from you, didn't show you the probability distributions, given that you can see the probability distribution, what's the right policy? What's the optimal policy? Yeah, just keep pulling arm number 3 all the time. Do action 3 all the time. You can't beat that, right? What's the expected payoff? About 1.5. Is there any reason to try one of those other actions if you know this distribution? No, because the expected payoff is lower for any other thing. Okay, so in a lot of cases, in fact, unless there's a tie, a deterministic policy is your best policy here. Okay? All right, now we're going to be interested in the case where you don't know what that is. So let's define a little simple terminology. Just like before, we'll say there's a Q function, although now we're going to not make it a function of state because there is no state. But the Q function is literally the expected reward that you'll get for any given action. And we'll use V star again to represent the optimal value that you can get. And so V star is just the maximum over the possible actions of the value of the expected reward. We'll define the regret for taking a particular action in one step as just the difference between the best reward you could have gotten in expectation and the reward that you actually do get from choosing your possibly optimal, possibly suboptimal action. Okay, and then if you get to pull the arm multiple times, then we'll say the total regret is just the sum of the instantaneous regrets. And a lot of the formal results about bandits and about, to some degree, reinforcement learning really is about trying to come up with algorithms where you can prove some bound on what this total regret will be. You see why it's called regret? Like, it's the difference between the reward you could have gotten if you had known the optimal strategy initially and the reward that in fact you get with your strategy. And of course, if you don't know the reward distribution in advance, then obviously you're going to have to, unless you're really lucky, in expectation, you're going to have some non-zero regret because there's going to be a learning curve where you get better and better at your policy, but while you're learning, you're probably going to be performing suboptimally. So when we get back to the question of exploration versus exploitation, it's really a question of how do we minimize this total regret? How do we play this trade-off between exploring and exploiting in order to minimize the total regret? Yes?
Is regret the same thing as like what we'd be calling as advantage in the previous lecture?
Of what we'd be calling what?
Advantage.
What we called advantage is a little bit different. It's very closely related, but when we said advantage, we meant if you take an action in a particular state, how does that change the value of the state you end up in? I mean, then what's the difference between the value of the next state and the value of this state? And this is just a little different, mostly because there is no state here. But modulo that, it really is pretty much the same idea. Okay? All right, so there's our terminology. One more bit of terminology. We'll talk about the count, the number of times that you choose an action over the window of time that you're playing. And we'll talk about the gap. And the gap is the difference between the best value you could have gotten and the value you get if you choose action A. So you can think of, for example, if you knew that, what did we say, action number 3 was the best one in that plot we're looking at? Okay, so the difference between the value you get if you do action number 5 and what you could have got if you do action number 3 is what we'll call the gap for action number 5. So it's the difference between your expected reward and the expected reward you could have gotten if you had chosen the best action. So we can then talk about the total regret is just the expected sum over the different times you play of this instantaneous regret. And if we take that expected value, rearrange it, I can write it this way, where n here is just the count of the number of times that action A has been selected up to time t. And so the total loss from 0 up to time t is just the sum over all the actions of the expected number of times you play each action times its gap. Right? So when you play the optimal action, this gap will be 0 by definition. And for all other actions which you regret having played, there will be a non-zero gap. By the way, why can I get away with bringing this expectation? Why didn't I put the right bracket over here instead of here? It's because we've defined V and Q in expectation already. So V is the expected best reward you could get if you play the optimal policy. So we've already defined V to be an expected value, and similarly Q, it's the expected reward. If those rewards, for example, are Gaussian distributed, then the expected reward is just the mean. And so that's why I only need to take the expected value of this. And what's that expected value over? Well, that's over my policy. If I have a stochastic policy for choosing an action, or even a deterministic policy that's changing over time, then based on the outcomes of earlier plays, then this is an expected value over that. And since I'm using delta to represent the gap, I can just rewrite it this way. Okay, and this is just going to be useful notation in thinking about different policies and their expected regret over the entire period of time from 0 up to t. So that's why we're introducing this notation. Okay, now of course the problem would be trivial, but we don't really know the rewards and therefore we don't know the gaps. And so it's all about how can we learn by exploring and exploiting. And theoretically what we'd like to do is characterize different learning algorithms that trade off exploring and exploiting, characterize them in terms of what is their total loss, starting from 0 up to time t. What's their expected total loss? Okay, so it turns out, for example, we've talked previously about epsilon greedy algorithms that, well, maybe wait till I get to the detailed slide, but we're going to see that there are different kinds of algorithms that give us different performance in terms of the total regret that they accumulate in expectation. And some of them will be linear in the total number of time steps, but our goal is to try to get things which have regret which is sublinear in the amount of training that we do, the amount of experience we collect. Okay, so let's start with the simplest thing, greedy algorithm. Just consider the algorithm that we estimate Q for each action. Again, there's no state, so estimating Q is very simple. We just get the sample average. If NT of A is the number of times that we've chosen action A from 0 up to time t, then all we really want to do is take the average reward that we get whenever we actually chose at time I to use action A. So, and this notation 1 of this thing just is an indicator function. Its value is 0 if the predicate in the middle is false, and the value is 1 if the predicate in the middle is true. So this is just a way of saying, count up all the rewards we receive whenever the action we chose was actually action A, and then divide by the number of times we chose action A. It's just the mean. Okay, so we can just keep playing and learn this simple version. It's a reasonable strategy for learning Q. And then the greedy algorithm, after having tried each action a few times, then after, we'll call that the burn-in period. After that, it just selects the action with the highest estimated Q value. So is that exploring or exploiting? Right, the burn-in part is exploring, but after that, it's pure exploitation. You're just saying, okay, I tried each restaurant 3 times, and now I'm just going to go with the one that I had the best experience, and I'm going to go there forevermore. So that'd be pure exploitation. Restaurant's not a good example, is it? Then we could have the epsilon greedy version of this. Yes?
For the greedy algorithm, doesn't it somewhat depend on like what you set your Q values as? So like, what if you set your Q values initially as really optimistic, and then over time you found that they weren't as good as you thought, and then as long as you keep on selecting the best one, then you'll be doing kind of both exploration and exploitation.
Yeah, that's a good point. So we could do that. But the way we've defined our Q estimate here, this is our learning algorithm for learning Q. And so we're just taking the sample mean. What you were talking about of having some initial kind of prior, you could think of it as a Bayesian prior, we'll get to that. But in this case, we're talking about this completely reasonable, unbiased estimator of the Q value. But your point is a good one. We'll come to that. Okay, so now we can modify this, and instead of having pure exploitation, we could make it epsilon greedy, which an idea we've already discussed, where, of course, what we do is with probability 1 minus epsilon, we choose uniformly at random an action, and then with probability epsilon, we choose uniformly at random in action. And with the rest of the probability, 1 minus epsilon, we exploit. So you can think of epsilon greedy as being epsilon % of the time we will explore uniformly, and 1 minus epsilon we will exploit. So if we do that, then we're blending with ratio epsilon, exploring and exploiting. And if you think about analyzing this, then you realize the loss per unit time, the loss on the teeth step, the regret, I should say, the expected regret is just going to be the gap, the sum over all actions of the gap of regret gap that we suffer for that action, which of course will be 0 for the optimal action, but non-zero for all the other suboptimal actions, times the probability that we're going to choose that, which is just epsilon. That's when we're choosing a random action, divided by the number of actions, because the epsilon probability of exploring will then be chopped up further into the k different actions that we have available. Okay, so there's the expected loss per unit time, written in terms of the gaps for each action, the gap between its expected payoff and the optimal payoff. And so in this sense, you can say, well, epsilon greedy is going to be linear in time in the expected total regret. That is, this is the regret per unit time. And you see, this is a constant, right? The number of actions is constant, epsilon is constant. The actual gaps, even though they're unknown to us for each action, are also constant. And so this loss per unit time is a constant, this expected regretted unit per unit time. And so if we do this across time, we're summing up, we're getting a linear expected loss with that coefficient. Yes?
The equation says that the expected regret is at least that constant, right? So
the
expected regret is at least that constant.
Yeah, this is at least, and why is that? Why is this not equal? Why is it greater than or equal? Right. So with one minus epsilon probability, we're going to choose the action that we believe is optimal. But it might not be. And if it's not, right, it's just the one that we currently think based on our estimate of Q is optimal. And so that's why I had to put a greater than or equal instead of an equal.
But it's still linear even though like it's just at least this constant.
Yes. So that means, well, that's right. That means it's lower bounded by a linear function. If you think about what's going to happen, here's a good question to ask yourself, or for me to ask you. If you ran this using our just maximum likelihood estimate of Q, like we talked about in the greedy algorithm, I'm just getting the sample mean for the reward for each action. If we actually run that, and we look at the difference between this quantity and the actual observed loss per unit time, does that difference between this quantity and the actual loss, that is the difference between the actual value and what I get if I predicted it to be this, does that difference grow, reduce, or stay the same over time in expectation?
Depends on if you are updating a Q value.
Yes, as I go, I'm always updating the Q value. So then it will reduce, right? Because over time, I will get a better and better estimate of the actual Q value. My estimated Q value will get closer and closer. It'll converge as 1 over the square root of the number of times I try it toward the true Q value. And so then I won't have that as frequently. I won't have as frequently the risk that I'm choosing a suboptimal action. Good. Okay, and here's the algorithm. It's actually very, very simple. We initialize our Q estimates and the counts for each action. And then with probability epsilon, or 1 minus epsilon, we explore or exploit. We observe what the reward really is. We update our count. We update our maximum likelihood estimate of the Q value. Oh, and I've written it this way. You'll remember that you can incrementally compute these means. You don't have to actually keep all the old data and recompute the same mean every single time from all the detailed data. You can just update your old estimate by adding in. If the reward you receive is actually equal to what you thought it would be, then you actually don't update the Q estimate. But if the reward you receive is greater or less, then you adjust your maximum likelihood estimate by a fraction of 1 over the number of data points you've now seen. So this is just the incremental way of computing the sample mean. So it's that simple. And in fact, if you do this on that multi-arm bandit problem that we talked about, here's what happens. This is averaged over several runs. But you can see what happens in green. We have just the greedy algorithm. After some short burn-in, and here you see the burn-in period, we then just keep exploiting. And so we don't get any better. On the other hand, if we do epsilon greedy with epsilon 0.1, we explore quite a bit and quickly reach a pretty good level. If we use a smaller epsilon, a smaller fraction of the time exploring, then we don't converge as quickly toward the optimal. We don't converge as quickly toward as good an average reward. I removed the word optimal. But as you can see, it's getting there. And what would happen what do you think would happen if I continue the curve out to here? Will it ever cross the blue line? Will it ever meet the blue line? Yeah, of course, it'll meet the blue line because eventually a smaller fraction of the time I'm trying the action I'm exploring, but eventually I'll explore enough to get to the blue line. Will the blue line, what if we go further? Will the red line ever cross the blue line?
Well, I guess at some point, since there's variation due to the epsilon, at some point due to random chance, the red line will be slightly above it.
In expectation, will it ever get above? Who thinks it will? Who thinks it won't? Okay, let's take a will. A will person can explain. Yes?
Eventually it's going to find that it really likes 3. And because it has such a small epsilon, it's going to stick to 3 much more of the time than the other one that has a larger epsilon.
Exactly. So you and I know that action 3 is the best action. And the blue line will probably figure that out, and so will the red line eventually. They'll both figure that out, that their Q estimate for action 3 will be highest. And so when they're being greedy, they will choose action 3. But when they're not being greedy, they're still going to choose uniformly at random some action. And this one is only going to do that 1% of the time. This one's going to choose a random action 10% of the time. So it's going to waste by exploring the opportunity it could have had to exploit. Okay? Good. So you see, this kind of suggests that maybe we should actually have strategies that have a changing epsilon over time, because once it knows, or statistically has high confidence that it knows the Q values for these actions, then it really should change to doing less exploring and more exploiting. All right, so we can look at that, but before we do, let's also take a quick look at non-stationary worlds. So we define the multi-arm bandit problem as we have defined MDPs as having a stationary distribution, both on the next state function, the effective in action, and stationary distribution in terms of the probability distribution on a reward. But in some domains, it's not stationary. And in fact, if you think back to the policy and value iteration algorithms that we actually use, we started out by talking about policy and value iteration as, well, we'll pick a policy, we'll evaluate it, meaning we'll run lots of samples and find out its value, and then we'll calculate a better policy from that. But then we quickly departed from that when we were talking about policy and value iteration, and we said instead, well, we can just update the Q function and greedily follow the new Q function. So we ended up interleaving the learning of Q and the using of Q. So we never really had a stationary state distribution from which we were sampling. And so that replay buffer that we have, for example, maybe has some very old stale data that's not representative of the state distribution we would get if we follow what we now think is the optimal policy. So there are cases even in the kind of algorithms we talked about for training MDPs where there's some kinds of non-stationarity. So what can we do about this? Let's take the simple case where, what if the reward function itself changes over time? Which would drive you crazy if you go to Las Vegas and start playing the gambling machines and they change, unbeknownst to you, the reward function. It would be even worse than Las Vegas currently is. Okay, but then obviously we might want to base our reward estimates more on more recent experiences to cover for the possibility that those distributions are changing. So again, if we say what we really want, if we had a stationary distribution on rewards, we would just get the maximum likelihood estimate of what the Q function is for each action. We can make the incremental version of it as we talked about. But here's an idea which is useful in practice. What if we keep the general form of this, but instead of updating our Q by the proper, if 1 over n, where n is the total number of experiments we've run, of samples we've collected, this is the proper way to get the maximum likelihood estimate of Q. But what if we just say, well, we'll use a different constant here? Well, if you expand this out, and in chapter 2 they do, you can see that you can rewrite this expression as being equal to this. And so now you can see what's happening is, again, n is the total number of times we've tried the particular action, and we're trying to get the Q value for that action. You can see what happens is the influence of the subscript here is the nth estimate of the nth reward we receive on the nth trial, and this is our nth estimate of the Q value. You see what happens is the very first estimate of the Q value gets weighted by this term which is, if alpha is positive, is exponentially decaying in time. As n grows, the number of times we actually play action A, then the influence of the very first experience is decreasing exponentially. And similarly here. I mean, we're adding up all of them with a similar, in a similar way. So this is a way, if we change that 1 over n to some constant which is positive but less than 1, then you can see we end up essentially weighting more recent experience exponentially more heavily than ancient experience. So that's kind of a nice, simple way to adjust your algorithm to make up for the non-stochasticity if you have it, non-stationarity if you have it, sorry. And there's a detail on this, which we can even make that alpha itself be a function. It doesn't even have to be a constant. We can make it a function of both the time step and the action. So we can use a different alpha for each one of those if we want. And we'll still get convergence so long as these two properties hold. And you can think of the properties as requiring that the alphas must be big enough that the initial random data that you saw gets eventually completely overwhelmed by other data because these things sum up to infinity. But they must be small enough that you'll actually converge, and so the square of that must sum to some finite, must converge to some finite sum. So this is a theoretical result. We're not going to prove it, but it kind of gives you an idea of what flexibility is available to you in terms of replacing that 1 over n in the incremental computation of maximum likelihood estimate by a constant or even a function of n and the action. Yes?
Does this mean that after a long time we start weighting like really old experiences a lot because alpha turns really close to 0? Or
No. This just says that the sum of these must be finite. It doesn't say how you distribute them. You can make the old ones, you can make the old alphas big and make the later ones small, or vice versa. It's just the total sum of all those alphas.
I mean, like, if we consider alpha as like how much we weight the current experience vs how much we weight old ones, then a very small alpha means we care a lot about older experiences compared to the current time. So it's like, if we're in a non-stationary world, we'll be caring about the rewards from a long time ago.
No, I think that's not, in this case, we're actually, okay, so in this case where alpha is constant, then yes, ancient experience is going to be ignored, not emphasized, but ignored, right? Because you see the exponential decay of that. This is going to be a number less than 1. It's going to exponentially decay in n. Here we're saying we could actually replace that alpha by an arbitrary function of n and a. I think what you said would be true for some choices we could make for this function, but not for all. Right? This is not making any assumption about whether a sub 1 is bigger or less than a sub 100. It's just saying the total sum of all those coefficients has to have an infinite sum, and the square and their squares has to have a finite sum.
It does mean it has to tend towards 0.
It does mean what?
That the limit of alpha as n is infinite is 0.
The limit of alpha
Like alpha sub n as n becomes very big, I think it's close to 0 otherwise.
becomes very big as n grows? No.
Alpha goes very small as n becomes very big. Otherwise, the sum of the squares can't possibly be finite.
The total set of alphas has to have some small things in it. But it's not the set, not the sequence. That's the difference. So this is not saying which ones have to be big and which have to be small. It just says the sum over the set of them has to have this property. So it's not telling you whether you should weight the original ones or the late ones differently. Okay. And so now we can go back and modify our epsilon greedy algorithm very simply just by where we used to take 1 over the number of times we tried the action, we can use our function. So again, algorithmically, this is very straightforward. Okay, but back to stationary worlds. That was just kind of a sidelight to talk about non-stationary. Let's come to the point that you were mentioning earlier of optimistic initialization. So this turns out to be a good practical thing to do. Instead of getting the maximum likelihood estimate of Q just using our observations, we could initialize the value of Q to some optimistic number, some high value, and then update as we always would. So if you think about it that way, you realize this is just like getting the maximum likelihood estimate from the observed data plus one hallucinated data point that we started with. And if you think about that, and you've taken the machine learning course before, then you know that's just a way of getting, instead of a maximum likelihood estimate, a Bayesian estimate where you put a prior on the, a particular kind of prior on the parameter that you're trying to estimate. But anyway, this is a good idea in many cases. We'll still update, as always. It's just that we start out with this initial value that corresponds to having a hallucinated initial example. And you could imagine modifying this to have multiple hallucinated examples, which is like putting a stronger prior. But then just update. And if we do this, what it does is it encourages exploration early on, because if we have, let's say you saw that plot of what the real rewards were. They were all like, the means were all below like 5. So what if we start with an optimistic estimate of 100 for every action? Then what's going to happen? We'll pick some action, we'll try it, we'll be disappointed because the reward we receive is actually going to be much less than 100. And so we'll update its Q estimate by lowering it. And now we'll pick an action, but we're not going to pick that one. So now we'll pick one of the others where we're overly optimistic. So we're just going to force ourselves to keep trying the ones where we're overly optimistic until they get brought down to reality by hard-lived experience that bring our estimates down to the real thing. So what this does, you can see, is it has this influence that it encourages exploration early on, but then things get better. Now, of course, if we have a purely greedy algorithm, after some burn-in period, it still might not have settled down to the right values, and we still can have a lock into a suboptimal action. So here, in fact, is in blue the optimistic greedy algorithm. Okay, so we initialize every action to the value of 5 here. And then we don't have an epsilon. Epsilon is 0. We're being greedy. But we're being greedy relative to our incorrect optimism. And so we're actually doing a lot of exploring early on, after which we greedily effectively get more realistic estimates of Q. On the other hand, if we compare that to a non-optimistic, realistic epsilon greedy algorithm, where we really do get maximum likelihood estimates of the Q values, then you see it takes us longer to do well, but things do improve over a longer period of time. Will this gray curve ever meet the blue curve? Who thinks yes? Who thinks no? I'll choose a no to explain.
Maybe because of what we discussed earlier, like you're always going to choose a random action with some probability. So if the optimistic initialization algorithm doesn't do that, it might do better than the epsilon greedy algorithm.
That's good. Yeah, so in the end, asymptotically, we're going to be exploring with probability 0 with the epsilon 0 one. Whereas this one, we're going to be exploring 10% of the time. And so even after we've converged toward good estimates, we're going to be still suffering regret because 10% of the time we're just acting randomly and we don't need to do that. So in this case, the gray will not meet the blue. Yep.
In this case, though, it looks like the blue curve is like plateauing around 80%. I'm not sure why that would happen. But if the realistic greedy is only doing the random action 10% of the time, wouldn't it go higher if that's where the blue curve gets stuck after doing exploration?
Yeah, you're right. That's a good point, which I had not noticed. What's going on? Help me. Yes?
So I'm also wondering about that. But so if we're still on the same 10 test bed, then it seemed that the two best actions were very, very close in the value. And so it might be possible that if they're close enough, it's actually like sometimes switching between each other. So if the values are very close and the variances are very big, it's going to keep estimating with one and the other, and like not figure out for a while which one is the best.
Yeah, that's a great explanation.
It's still 1,000 time steps though, so like it seems like a lot.
The problem is that your exploration is 0%. So if you happen to get, you're going to have high variance estimates of these Q values as you get started because you don't have enough samples. And if you get into a situation where, like you say, maybe the true value, which you don't know, of one action is just a little bit higher than another. But if you happen to get a sample of data where you're underestimating the value of the good one, of the better one, but you have a representative sample and you're getting an accurate estimate of the second best one, you're going to turn off, you're never going to explore. So as soon as that optimistic value comes down, it's possible that it'll actually go below its true value. In which case, if it goes below the estimated value of a different action, basically you're locking out ever experimenting to find out a better estimate of the top action. So that's why, thank you. So that was a good repair of my misunderstanding. But so that's, and that justifies the comment on this earlier slide. Optimistic greedy can still lock into a suboptimal action. So. Okay, so in that case, I guess we have to say, if taking into account that the blue curve is appearing to being asymptoting around 80%, I take it back. The gray one might actually get up to 90% of what it can do because it'll eventually converge toward accurate estimates of all the Q values, which would give it 100%, but then it's going to be exploring 10% also. Okay, now another idea, of course, is that we could have epsilon decay over time. And there's a nice little theoretical result here, which says, suppose we use this strategy. Let's say C is some constant. D is the smallest non-zero gap. Now, what does that mean? That means if we take the best action and the second best action, then D is the gap between those. It's the difference between their expected values. And if we use this schedule for epsilon, then it's possible to prove this has logarithmic asymptotic total regret, no longer linear. So what's going on here? By the way, this is not very practical because we don't really know what that gap is. So we don't know what D is. So in practice, we can't really use this because it's not until we know Q that we know what D is. But if we could do this, what this is saying is epsilon, of course, can never go above probability 1. But what this is saying is the more actions we have, the bigger epsilon should be. That makes sense. We want to think in terms of number of examples per action, not total number of examples. As time increases, we're going to decrease as 1 over t. That's our scaling of this epsilon. And then d squared, what does that mean? That means if we take this gap, the smallest non-zero gap, as that gap shrinks, we're going to need a lot more epsilon. This ratio is going to grow. So as the gap gets very, very small, we're 1 over a very small number squared. So as that gap shrinks, this quantity is going to grow. Does that make sense intuitively? Of course it does, because if my best action is here, my next best action is here, but in scenario 2, the best action is still here, but the next best action is almost there, I'm going to need a lot more data, a lot more samples to be confident of which of these two very near, very close reward actions is best. Whereas if the gap is big, then I'm not going to need so much data to have the same kind of confidence. So it makes sense, and it shows that there is a way of getting logarithmic expected reward, but you have to unfortunately know in advance this quantity. Okay, so a kind of related idea, which can be implemented, unlike the previous one, is to use upper confidence bounds. So what if we say we have our maximum likelihood estimate of Q, just the average reward we've seen for each action. But statistics tells us that we can put in upper bound a confidence interval. So, like if you flip a coin k times, and it's going to come up heads or tails, we have confidence bounds that tells us as a function of how many flips, n, how far is our estimate, our maximum likelihood estimate, going to be from the true value. And as n, the number of flips, grows, then the probability distribution over our estimate becomes sharper and sharper, and our confidence bounds become smaller and smaller. So we can use that idea, and then we can use we can look at basically the sum on the right here and use that sum as our basis for choosing which action to try. And when we have a little bit of data, the upper bound, the U term will be wide, will be big. When we have a lot of data for that action, it will start shrinking. And so this is a way of encouraging us to explore actions where we have most uncertainty about the true Q value. And yeah, as I said, here's the action. I'm just going to choose the action that maximizes the right side of this, the upper bound on for some confidence level. Okay, so just to illustrate this, suppose that I'm a Bayesian, and I want to know the probability. Let's take action A3. I've gathered a certain amount of data, and the mean of that data is apparently 2.45. That's the most probable value for Q, given the data that I have. But given that I only have a finite sample of data, there's some probability that the true value of Q for action 3 is 2.8 or maybe 2. And those have different probabilities. And similarly for all the other actions. And so if we use, let's say, the 90% confidence interval on these, like the green curve, the 90% confidence interval means what's the value of Q for which 90% of the probability mass here is for the value of Q to be below there, and 10% probability it's above that. And so that would be around here, whereas for the blue one, it'll be over here. So even though my best estimate for the Q value for action 1 is about 1.3, and my best estimate for action 3 is about 2.5, if I use this upper bound, then I'm going to say, well, when I add in the upper bound, it's for the blue curve, it's over here where 90% of the probability is below, but there's still 10% probability that the true value of action 1, even though my current estimate would put me here, there's some probability, because I haven't seen that much data yet, that the true value of the blue action is at this level. And so I'm going to choose that and do it. I'll explore. When I explore and get more data, what happens to the width of the blue curve? It sharpens, right? It gets smaller. And more data gets sharper and sharper. Asymptotically, it becomes goes toward a point estimate. And so it's the width of these curves that we're going to use to capture the uncertainty and whether what we should explore with. Now, there is this little technical detail. How can we actually calculate this upper bound if we don't know the form of the distribution on the Q function? And the nice thing is, Hufting's inequality. If you've taken a course in machine learning, you probably have already experienced Hufting's inequality. If you have not, every person who leaves CMU with machine learning in their resume should know Hufting's inequality. It's really important. And it's beautiful because it's so general. You can apply it in many cases, including to estimates where you don't know the functional form of the distribution that's governing your variables. Let's see what it says. Let x1 through xt be independent, identically distributed according to some distribution which we don't know, random variables in the continuous interval, a real number between 0 and 1. And let xt bar be just the sample mean, the maximum likelihood estimate of the mean for those variables. Then, despite the fact that we have no idea what the underlying distribution is on these x variables, just that they're all from the same distribution, we can say that the probability that the expected value of x, that is the true mean of that unknown distribution, this is the true mean of that unknown distribution, the probability that that true mean is more than our sample mean by an interval u is bounded by this much. And what's that? This is e to the minus 2t u squared. U, of course, is our interval, our upper bound interval. So as that grows, the probability decreases, e to minus u squared. So the probability that it's within 0.1 is less probable than the probability that it's within 0.9. As u grows, this probability drops. And t, what's t? Oh, t is the sample size. So the more samples we get, remember they go from x1 to xt, the more samples we get, the lower the probability that our estimate is worse, the lower the probability that our sample mean deviates from the true mean with margin u. So Hufting's inequality is just beautiful. You can use it in so many ways. And we're going to use it here. So we're going to say, okay, then the probability that our maximum the probability that the true Q value for action A is more than our sample mean, our maximum likelihood estimate, plus some upper bound UT is bounded by this. So now all we have to do if we want to implement an algorithm is we just pick a value for this bound. We say, well, I don't want that to happen more than 5% of the time. And now the algorithm that simply, oops. Let's go through it here. Then the algorithm that uses this will be, we can bring in Hufting's inequality to calculate that. Okay, so let's see how we do that. Suppose that suppose we solve for, we set our probability. I don't want that to happen more than 5% of the time. So I set p to 0.05. Now, if you just solve this, you get the upper bound is this. And again, this is the number of times we've tried action A. So it's good that our upper bound shrinks if we want the 5% at worst bound. This is going to shrink as the number of examples grows. And if we want 10% instead of 5%, then this is going to be larger. Okay, so that's the idea. And then for example, if we say that we want that probability p to go as the number of steps t to minus some constant, let's pick c equals 4, then if we plug in that for p equals t to the minus 4, then we can get a very direct solution for the quantity. How much should we look? Instead of using our estimated Q value, we should use our estimated Q value plus this quantity if we want to make sure that with probability p, probability at most p, the true value of Q is below our upper bounded version, the maximum likelihood plus this. Okay, so this gives us a way of just calculating basically those confidence intervals in a way that's agnostic of what the underlying distribution is. And so that leads to a very simple algorithm. We take the action that maximizes our current estimate of Q plus this upper bound quantity. And as we get more and more examples, that upper bound quantity shrinks and goes away, approaches zero asymptotically, and we default back to the exploitation strategy of using just our estimate of Q. But in the early game, where we have very few examples, just one, say, then this upper bound is going to put in that kind of optimism. And because this is based on Hufting's inequality, it's a justified schedule. And in fact, it satisfies what we wanted, which is a practical algorithm that gives us logarithmic asymptotic total regret. Logarithmic in time. So t is the number of steps that we've taken, and you see it grows as the log of that. And then this is, again, a constant. Those gaps are whatever they are, even though we don't know them. But it's a constant, and so you can see that the total loss from time 0 up to t grows only logarithmically in t. Cool, so this is actually very nice. So it's an upper bound algorithm. instead of using our estimate of the mean, instead of taking our maximum likelihood estimate for Q, we take that plus some upper bound interval that corresponds to a certain probability of our estimate being off by that much. Okay, so if you try this in practice, here's a plot, again on the same 10-arm bandit problem we looked at before. And you can see this upper bound UCB algorithm, in this case, outperforms epsilon greedy with epsilon 0.1. It's not that different in this case, but it is better. I'm going to skip that. Okay, so now that we're kind of into the idea of using statistics and confidence bounds to actually estimate when we should exploit and when we should explore, we should look at another approach called Bayesian bandits. In some cases, we may know something about the form of the probability distribution on rewards. So in that case, we can use Bayes' rule. Sorry, go ahead.
I was just wondering when we used that assumption of the bounds on the rewards previously.
Mm-hmm. That one?
So is the assumption that the sum of the bottom is bounded, or?
Yes.
Could it really not be?
Well, let's see. This is a constant. That's a constant. So the only question is the sum of log t from 0 to infinity. I sure hope that's bounded.
So what was the assumption we made, and how did we use it then? Because so the slide said that we assumed that that we assumed something on the distribution of rewards.
Oh. No, we made no assumption about the distribution of rewards, which is why we fell back to using Hufting bounds, because they give us a distribution-free bound on the probability that the true Q value, which we're trying to estimate, is off from our maximum likelihood estimate by at least this much. That's what Hufting bound is.
I remember this. I was just wondering, so on the very last slide that we see, there's
This one?
the slide says that no, like where we were currently. Sorry.
This one and then back?
No, like when you switch to Bayesian bandits.
Uh-huh.
You said that we had made no assumptions about the reward distribution except for the bounds on rewards. And I just didn't remember us making an assumption on the bounds on the rewards. But maybe I'm misremembering.
No, we did not make, I'm sorry, I shouldn't have, that line is a misleading line. I shouldn't have, we have not here made assumptions about bounds on the reward. I guess, have we? Oh, they're between 0 and 1. That's right. So the Hufting, thank you. The Hufting bounds, the way we stated the Hufting bounds, they assumed that the quantity we're trying to estimate is between 0 and 1. These are random variables in 0, 1. On my feed, I don't know what to say about how you would adapt to non-zero 1. But that would be an excellent homework question. Then you could teach me. Yeah, so on my feed, I don't know what to say about if it's not in 0, 1. Do you?
On this one, but I'm pretty sure this can also be in -1 or something. We use exactly this thing for Monte Carlo research, where we have the win, not win of the game. So I suppose that was 0, 1. But there were also, you could win double game. So in this case was 0, 1, 2 or something.
Yeah. I'm pretty sure I've seen a version of Hufting bounds that says it's between A and B for arbitrary A's and B's. But again, I'm standing here, I can't give you that.
Like even if, I see how we could generalize this to between A and B by just gaining distribution. But like the normal distribution isn't bounded in any way. There's a bit, I feel like
yes.
straight bounds and
That's right. Well, that's right. The normal distribution is unbounded, but we're not saying let's see what exactly we are saying. Yeah, this says the random variables are themselves bounded. So yeah, if it's a Gaussian distribution, the random variables are not bounded. So that's an issue. Yes?
I believe if the random variables are bounded to A and B, then you can divide by B minus A.
I think that's correct, which still doesn't, unfortunately, cover the Gaussian case.
But then, I mean, if you said straight-faced, oh, it works for Gaussian distributions, I would definitely believe that.
Yeah. You only get in trouble very rarely.
Yeah, like all on the other side.
Right. But good point, and good catch. Let me finish up by looking at one more idea, and then we'll continue this next time. So suppose we do know the form of the reward function. For example, suppose we know it's Gaussian, although we don't know the parameters of that. We don't know what the mean is. We don't know what the standard deviation is. Still, as long as if we're willing to put down a prior on what those mean and what mu and sigma, the mean and the standard deviation are, then we can, as a Bayesian, solve for, if we put down a prior on what that distribution of rewards is, what the parameters of that distribution are, then we can solve for the probability distribution on those parameters, given the experience we actually see, get the posterior. And then we can use the same kind of UCB algorithm, but now we're not relying on Hufting's inequality. We're simply using our greater knowledge of what the distribution form really is. So we can do that, and just to illustrate, suppose that we do know the distribution for each action, distribution of rewards for each action is a Gaussian distribution. It's non-deterministic. So we pull the lever, same lever several times, we might get different rewards, but it's Gaussian distributed. Then it's not hard to work out what if we have some prior probability we're willing to assign to the mean and standard deviation of each action, then the posterior, the probability distribution on those same parameters, which will be different from the prior, given the experience, is simply that prior times the data likelihood. The product over all the time ticks we've gone through of the probability under this normal distribution of observing the actual reward that we got, given those parameters. So this is just Bayes' rule, but it says that we can get the posterior distribution on mu and sigma for each action. If we start with a prior and look at basically the data likelihood. And so in this way, we can actually literally compute what these curves are. We can estimate, initially they'll just be the prior distribution. But then we can get a posterior, and we can solve for these distributions. And then, again, we can pick the action that has the maximum, again, upper bound. So we're going to take the mean reward for this action, plus some constant times the standard deviation. And this is normalized, again, by 1 over the square root of the number of samples that we have. And this assures that as the number of samples grows to infinity, this term shrinks to 0. And so we end up, in the end, again, simply exploiting. But now we're using the calculated variances of these distributions to guide our exploration as we go. So this is just like, the logic of this is just like the logic on Hufting bounds, except that now we're taking more advantage of more knowledge that we have, which is the form of the reward distribution itself. Okay, so I think I'll end there because I'm going to give Katerina a chance to say whatever is on her mind. And we have a few more things to say, which we'll say next time.
What I would like to ask is, what if we don't know the form of the distribution, which is most of the time the case. You don't know the distribution of your reward function. You don't know, and these are bandits. No, so in the next class, once Tom does his initial wrap-up, we're going to talk about exploration on beyond bandits, right? We're state dependent. Here we're not state dependent, we just sample the same action. And we're going to build Q functions, and these Q functions can be extremely complicated. And you saw that it's extremely important not to just keep track of the expected value, but rather also your uncertainty. So once you're building a Q function approximation, right, in some places of your space, this Q will be very certain because you've seen lots of data from that space. And in other parts of the space, it's going to be quite uncertain, okay? So far, we have been feeding one neural network, and which is similar to a point estimate here, right? It's like the expectation of the weight. We just take one we don't consider the distribution of the weights of the neural network. We just consider one snapshot of what gradient descent gives us. And we have no way to know when these Q estimates are certain and we should trust them and when they are certain. And why this is important? Because as you saw here, you can just explore by keeping track of your uncertainty. Essentially, if we were able to keep track of the distribution of Qs, each time what we would sample from this distribution and follow as if this Q is correct, and collect new data and update our model, okay? So in this way, when you're more uncertain, this is where you spend your efforts exploring, and when you're certain, you just exploit, you don't explore, okay? So we're going to talk about this. We'll discuss how we can encode this uncertainty in neural networks, what are the more formal way of doing it, what is a more computationally tractable way of doing it. So we'll see a lot of different solutions that you can take. We will talk about uncertainty not only on the Q functions as here, which is this what essentially we're doing, but rather also on transition functions, okay, on predicting our dynamics. So we'll try to explore by building a model of the environment and try to make as much progress on this model, and these are all equivalent notions, maximizing my learning progress, minimizing my prediction error, maximizing the information gain from the next transition. We'll see how all these are equivalent, and we will show at the very end how you can just win Atari games without any extrinsic reward, simply by having as a reward this exploration bonus that tells you, I want to make my predictive model to fail. So you're playing so that you can surprise as much as possible the predictive model of the environment that you're building without knowing anything about the score game, without knowing anything about when you die, okay? So this will show how important exploration is in all this. We will see it as our empirical, how to say, evidence will come from Atari games, but in robots also is going to be the same. Okay? That's it. See you next time.